Good afternoon. Today we are having a lecture at a slightly different time. As I see, no one is here present in Zoom, so probably there is something with notification going on. I am going to figure it out after the lecture today. Today the topic of the lecture is fluctuations. As it is, this topic is very difficult, so we are not going to give a complete theory which describes fluctuations in any thermodynamical system. Instead, I'm going to tell a few stories which can give you an impression about how this branch of thermodynamics and statistical physics works. And I would like to start with a very simple problem. The fluctuations are already inside the distributions we have studied previously. For example, in Maxwell's distribution. So the first story I'm going to talk about is the mean energy and fluctuations. Mean energy and the fluctuations of energy in the Maxwell distribution. So as much as we know about Maxwell's distribution, it appears that the particle has the probability to have certain velocity with the following probability density. There should be some sort of a normalization constant, and I'm going to write this normalization constant as 1 over z, since we have already the concept of partition function introduced. So that's 1 over z times the exponent of minus mv squared over 2kbt times times the element of the velocity space dvx, dvy, dvz. Essentially, that is the Maxwell distribution. And now I'm not going to determine the mean energy of the translational motion like we had done so in the lecture devoted to Maxwell's distribution. I'm going to use the statistical physics approach, in which I first determine the partition function and then derive all the values from that partition function. So by definition, the partition function should be a sum over all available energy levels of the following exponent: exp minus the energy level over kbt. In our calculation, we have when we talk about the translational motion, we actually mean the continuous distribution for energies, so that's why this distribution should be replaced with the following normalization integral, which is exp minus mv squared over 2kbt times dvx, dvy, dvz. So that's going to be the partition function for this system. And we need actually to use the integrals of these exponents which we have introduced before. And I am going to remind you that we had the function f of n, which is the integral from 0 to infinity of exponent minus a s squared over 2 times es times Okay, actually s to the n. And we know that actually f of 0, the one which is the most useful for this part, is equal to this integral, which is square root of pi over 2a, as far as I remember. So if we apply this to this integral for the partition function, and we see that this is actually a triple integral, and which can be decomposed as follows. This is a cube of the integral from minus infinity to plus infinity of exponent of minus mvx squared over 2 times dvx, and to the third power. So I have written here only the integral for vx and have written the third power, but of course I mean by this that we have vx, vy, and vz, and since all of these integrals are in all of these integrals, the only thing we do is we just change the variable of integration, the notation for the variable for integration. That means that all of these three integrals are equal to each other. So from this we get that it should be twice f of 0 cubed. The factor of 2 comes from the fact that here the limits of the integration go from the minus infinity to plus infinity, while in this function the limits are from 0 to infinity. That's why, and we have actually an even function, so that means that this integral is twice the integral from 0 to infinity. So that's why we have this answer. So altogether that gives us actually something like let's say square root of 2 pi over, okay, instead of a, we have actually kbt over m, so that would be something like this. And well, since we have energy here, so well, whatever. So it would be just 1 over a, which is actually kbt over m. So a is m over 2 kbt. So that would give us something like this, and again cubed. Okay, so from this we can actually rewrite this equation as follows. Usually we write the partition function as a function of the reciprocal thermal energy beta, which is 1 over kBt. So in here it can be written as follows: that the square root of 2 pi times over m beta cubed. So essentially this is some constant divided by beta to the 3 over 2. So from this we are going to determine the average energy, and the famous formula says that the average energy associated with this degree of freedom should be calculated as minus 1 over z times dz over d beta. If you have, for example, forgotten why this equation is valid, actually, then you can always rederive it using the the definition of the partition function. So according to the definition of the partition function, that's an exponent of minus beta ei. So if I calculate the derivative of this function over beta, that would give me sum over I of ei times exponent minus beta ei. So in order to get the average energy, I need to multiply, okay, I have also minus sign here. I need to multiply this by -1 and divide it by z in order to convert this exponent into the actual probability to have that energy. So that gives me that average energy is -1 over z, dz over d beta. Or actually it can be written as follows: minus d natural log of z over d beta. In here, I use that dz over z is actually a d logarithm of z. So in here, if I calculate, for example, using this second equation, minus d natural log of z over d beta, if I take natural log of this expression z, that would give me -3/2 times natural log of beta. So that means that the answer is actually -3/2 multiplied by the derivative of logarithm beta, which is actually 1 over beta. And after I substitute again that beta is a reciprocal thermal energy, that will give me that this is actually equal to 3/2 times kBT, and this is the well-known value for the thermal energy for the translational motion. Okay, so that's not the end actually, because we need also to determine the fluctuations of this energy, so or variance of this energy. So I'm going to go to the next blackboard here. So the variance of energy E should be, by definition, it should be average of E squared minus the average energy squared. So how we are going to determine the average energy squared? So we are going to use the very same concept that we have employed previously for the definition of average energy. We are just going to calculate the second derivative of the partition function. So since the first derivative gives you something related to energy, then we should expect that the second derivative of the partition function would be something related to the squared energy. So we have here the sum of exponents. So if I take the second derivative here, denoted by these two primes, so I have an exponential functions in our sum. So if I take the sum first and then calculate the derivatives later, so that means that each of the exponent produces the factor of minus e upon each calculation of the derivative. And this factor comes from the chains rule, so this constant is independent of beta. That's why we have just to multiply by minus e twice. So that would give me eventually, actually, well, I can change here minus to plus because I have energy squared. So I have this one, and what's left for me to do for calculation of the variance of energy is I just need, to calculate the average square of energy, I just need to divide all of this by z. Okay, so now I have it written like follows. So if I add up also the average energy squared, so that is something like -1 over z, dz over d beta. And actually, I can calculate a compact expression for the variance if I use some well-known rules for the calculation of derivatives. So let me write it here. So according to this equation, variance is something like this. So if I use this, and then I'm going to have the following. That the variance of energy should be 1 over z times the second order derivative of z over beta minus, and here goes this term squared, which give us 1 over z squared times dz over d beta. If I look at this expression, then it somewhat reminds of the calculation of the derivative of the product, because as you see here, we have a second derivative here. Okay, now it also should be squared, but in here, actually, we have essentially the derivative of 1 over z multiplied by the derivative of z over beta. So I'm going to use this fact. So to show you explicitly how it works, I'm going to write it like follows. And this is 1 over z times d over d beta of dz over d beta. Then I add actually this d over d beta of 1 over z. So essentially, if you calculate this, that would give you minus 1 over z squared times dz over d beta. But I have dz over d beta squared, so I should multiply this by dz over d beta. And at the very end, I actually see that this looks like the multiplication rule for the derivatives. So I can write it as d over d beta, the derivative over beta of 1 over z times dz over d beta. And once I take into account that this is actually the derivative of the natural log of z over beta, so what I actually have here is the second derivative of natural log of z over beta. Okay, so now I'm going to use this to calculate the variance. So now I'm going to calculate the variance of energy. Which is the second derivative of z, logarithm z. So as we have derived previously, the logarithm of z is some constant minus 3 over 2 times natural log of beta. So if I take my derivative twice, that would give me, if I calculate the first derivative, I have already calculated it here, it gives me just minus 3 over 2 beta, and then I need to calculate another derivative. That would give me minus 3 over 2 times minus 1 times 1 over beta squared. So that gives me 3 over 2 beta squared. That's the variance of energy for the single particle here. So now actually to give the result in a common variables, I need again to replace beta by the reciprocal kbt. So that gives me 3 over 2 kb squared t squared. That's the variance. Well, you might ask that actually it's not that important to understand the mean value and the variance of the energy for the single particle. It's actually much more important to have some value for the mean value and the variance for the kinetic energy of the gas as a whole system. So I need to go some way from energy and variance for the single particle to the energy and variance of the gas, which consists of multiple particles. So this question is actually the beginning of my second story today. The second story is how you calculate mean and variance or mean and fluctuations of macroscopic quantities. Usually, let's consider this problem in the general context, and let's assume that I have a macroscopic quantity capital X, which is presented as a sum of some microscopic quantities x1, x2, plus so on and so forth, until I have xn, where n is the number of particles in my system. What I'm going to use here is that, first of all, if I want to calculate the mean value of x, then I need to sum up mean values of all of these variables. And well, assuming that actually that all of the particles are indistinguishable, so all of these mean values are the same, and also I assume that these values are independent from each other, that the particles actually interact only weakly. That's why all of the microscopic quantities are essentially independent random variables. So that gives me capital N times the microscopic variable. So, okay, please know that in here I have capital X and here I have small x. That's the difference between them. And if I want to calculate the variance, I'm going to use the property which I have derived during the lecture devoted to the some basic stuff about probabilities and statistics, and in which I have derived that the variance of A plus B, where A and B are independent variables, is equal to the variance of A plus variance of B. Of course, this property can be extended to more than two variables, because if it, for example, if you have, for example, three variables, A plus B plus C, then you can write it as variance of A plus B plus variance of C. And again, applying the same property to the variance of A plus B, I would get variance of A plus variance of B plus variance of C. So that means that whatever the number of terms in my sum is, I can say that the variance of the sum is equal to the sum of variances of all of the terms of which the sum consists. So if I apply this rule to the macroscopic quantity x, that would give me that variance of x equals to n times the variance of a single quantity, variance of small x. And variance, by definition, variance is the squared deviation, a mean squared deviation from the mean value. And if I want to calculate the so-called standard deviation, or the standard deviation, which we take as the absolute fluctuation of the value, the standard deviation is the square root of the variance. So my standard deviation scales with the number of particles as square root of n times sigma of x. So this is the well-known square root of n law for the systems consisting of many particles. And if I want to calculate not the absolute fluctuation but the relative fluctuation, then I need to calculate the ratio of the sigma capital X over the capital X. So that would give me 1 over square root of n of the same quantity for the microscopic value. So this is, let's write that xi here in order to underline that this quantity is actually related to the microscopic system. So if I apply this approach to the system, to the ideal gas, and want to calculate the fluctuation of the energy related to the translational motion of particles, then what I actually need to do is to, first of all, I get that the average energy is n times the average energy of a single particle, which is n times 3 over 2 kBt. And secondly, if I want to calculate fluctuations of this energy, then I need to do the following. I need to calculate the square root of 3 over 2 times n times kb squared t squared. So that's the fluctuation of energy. Well, actually, I can take kbt out of the square root, so that would leave me with kbt times square root of 3 over 2n. And if I calculate the relative fluctuation of the translational energy of molecules, that would give me something like square root of 2 over 3n, which is approximately equal to 1 over square root of n. So as you see, if we calculate fluctuations of variables pertaining to the macroscopic systems, then all of these fluctuations tend to decrease as square root of n. And as you know, the typical value of n for thermodynamics is something like Avogadro numbers, so that would give you a really small relative fluctuation. Okay, so now let's continue to the next story. Let me... Okay, then in our next story, I'm going to calculate the variation of the number of particles in gas. The story number 3. Okay, so so before we start, I actually need to calculate to formulate the problem I'm going to solve. So let's assume that I have a very large volume filled with the gas, and I select a relatively small subspace of that volume, and I want to find out how many particles, how many gas molecules happen to be in that particular selected volume. And the problem is that actually the particles can cross the boundary of this volume. That's why this number of particles inside the volume is not a constant. It's a fluctuation number. So in order to find out the mean value and the fluctuation of that value, I'm going to employ the following approach. I'm going to, so let's say this volume is V0, and the full volume is V. The total number of particles in the full volume is capital N, and the number of particles inside that volume, which I want to determine, is actually in 0. And of course, I think one of the best approaches for these calculations could be presenting the number of particles inside that volume as sum of some microscopic values. But we need to carefully design such a microscopic value that some of these values would give me the total number of particles. So I'm going to do that as follows. I'm going to to assign a number to each of the molecules in there, and then calculate n0 as sum of x1 plus x2 plus so on and so forth plus xn. And each of these axes is determined as follows. Xn equals to 1 if the molecule number I, okay, xi equals to 1 if the molecule number I is inside the volume V0, and it's equal to 0 if that particular molecule is not inside V0, so if it's outside. Then, of course, if I sum up all of these numbers for all of the molecules inside my large vessel, inside my large volume, then that sum would give me exactly the amount of molecules which are inside the selected volume. So, of course, for each molecule, there is a certain probability for that molecule to be inside the selected volume and to be outside. And the probability to be inside is equal to the ratio of volumes, V0 over V. We assume in our, in here, I assume that actually the molecules move chaotically, and as they move chaotically, their motion trajectory spans over the whole volume. So, and this is actually valid, and that means that if the molecule is allowed to travel everywhere, then indeed the probability for that molecule to be inside that volume is equal to V0 over V. And the probability for the molecule to be outside is, of course, 1 minus V0 over V. So if I calculate the mean value of xi, that would be 1 multiplied by the probability for the molecule to be inside the selected volume, which is 1 times V0 over V plus 0 times 1 over V0 over V, which gives a V0 over V. Okay, now I need to calculate the average number of molecules in the selected volume. I need to multiply this by capital N. That would give me actually the well-expected result NV0 over V, which is actually the product of the number density of molecules by V0. Indeed, N over V is the number density of molecules inside my large volume. And my derivation postulates that actually this number density, average number density everywhere inside my vessel should be constant, which actually agrees with the Boltzmann distribution and for the equipotential profile inside the vessel. What's actually more interesting here is not the average or mean value of the number of molecules inside the vessel. This is just a very illustrative example that you can calculate that number correctly using this approach. What's actually more interesting is the fluctuation of this number. Okay, so now let's try to determine the fluctuation of this number. And one of the approaches to determine the fluctuation is that fluctuation squared is actually the variance of n0, and by definition, variance of n0 should be n0 squared minus average n0 squared. So, and according to the definition, n0 squared should be n times xi squared minus, okay, once again, and this is n0 squared, which gives us n times v0 over v squared. So what we are left with, what's missing in our equation is the average of x squared. And I'm going to calculate it by definition. So the average of x squared should be 1. Okay, if x equals to 1, then x squared is also equal to 1, multiplied by the probability, which is v0 over v, plus 0 times the probability 1 minus v0 over v. So in the end, that's the average x squared minus n squared v0 squared over v squared. So finally, we get n times again n times v0 over v minus n squared times v0 over v squared. Okay, let me see that once again. N times v0 over v, well, and that the number which goes into that side is average of this. And it turns out that actually some of these two numbers are very small. And let me see once again which one is small, which one is large. And we assume that actually we have quite a lot of molecules inside the selected volume. And it appears that I have somewhere done a small mistake here. Let me see that once again. 1 plus 0 times this probability, which gives me something like this. Let's try to adopt another approach for the calculation. So let's assume that actually, let's see where the difference comes from. Let's do it like follows. Let's do this by definition. The variance is actually the variance is actually the okay, so now I understand where this comes from. It actually, I cannot do this, but I cannot write that actually n0 squared equals to n times xi squared. So that's where mistake has come from. So this is actually wrong. So let's redo this calculation once again, because we got the wrong result. As I said, that actually this variance should be calculated as n times the variance of xi. And now for xi, I can write that should be xi squared minus average of xi. And minus average of xi squared. So that leads me to the following, that xi squared has the average of v over v0 over v, while the second term gives me v0 over v squared. And the second term, assuming that this volume v0 is much smaller than the total volume of the vessel v, then that would mean that actually that second term in here is very small. So it's almost 0 compared to the first term. So that gives me the answer n times v0 over v, which is exactly the number of particles. So that's a property of this ideal gas, of the distribution of the molecules of the ideal gas in a volume, that actually variance is exactly equal to the average number of particles in that particular volume. So that means that the fluctuation of the number of particles is exactly equal to the square root of n0, and the relative fluctuation of the number of particles in the selected volume would be 1 over n0, where n0 is the average number of molecules inside that volume. As you see, well, when it doesn't matter, actually, I use n0 and average of n0 interchangeably. So in these equations, actually, n0 stands for the mean value of n0. So as you usually do, like if you write the internal energy of the system, of course, that is actually the fluctuation quantity. But if you write it in your thermodynamic equations, what you actually mean by writing this one is the mean value of the internal energy. Okay, so that's the end for our third story, and let's have a short break before we continue. Yeah, let's continue. So in the previous part, we have ended up with the fluctuations of the particle number, and it turns out that the fluctuations obey the square root of n rule. So they are increasing as the absolute value increases as square root of n, while the relative value decreases as the inverse square root of n. In the first story, which I'm going to offer you during our lecture, is I'm going to somewhat generalize and extend the approach for calculation of fluctuations of energy, which I have used in the very first story for the calculation of the energy and the fluctuation of energy of translational motion of particles. So in here, I'm going to assume that I deal with an arbitrary system. It can be a system consisting of discrete energies. It can be the system which contains molecules, the ideal gas, non-ideal gas, whatsoever. Whatever system you have, it can be described by a partition function. So I start assuming that I know the partition function z. Starting from that partition function, I aim to determine the mean value of energy and the fluctuations of energy associated with this system. And as I have said previously, usually partition function is determined for the energy, for the system which is kept at the constant volume. So of course I'm going to determine the fluctuations of energy at the constant volume. But, well, actually that can be applied pretty much easily to any system. So in here what I'm going to do, well, I know that my z is sum of exponents of minus beta e I. If I want to calculate the average energy, as I have said previously, what we need to do is we need to determine minus 1 over z times dz over d beta times dz over d beta, which is minus d natural log of z over d beta. Once again, I'm going to use the same trick which I have shown you for the Maxwell distribution, in which I have calculated the variance of energy as the second derivative of the logarithm z. But now, instead of using this expression, I'm going to relate it to other thermodynamic variables. As you see, that actually what this quantity signifies, this is actually the derivative of the average energy with respect to beta. Since this is the second derivative, this minus derivative of average energy with respect to beta. So it becomes quite obvious that we should somehow relate this quantity to the heat capacity, because this is a somewhat transformed temperature. So this is actually what we are dealing with, the derivative of energy over the temperature. And by definition, the derivative of energy over the temperature is the heat capacity. But as you see here, there is some differences are present, because in here I have derivative of the temperature, but in here I have the derivative of some other variable beta, which is 1 over kBt. So I need to perform the variable transformation. So I know that beta is 1 over kBt. So I want to relate somehow derivatives over beta and derivatives over t. So what I'm going to use, I'm going to calculate the differential of beta, and that gives me d beta gives me 1 over kb times dt over t squared, and I also need to have a minus sign here, so I add minus 1 over this. So that means that I can substitute this instead of d beta, and this minus by this minus gives me plus, and altogether that gives me kb t squared of derivative of average energy over the temperature. And this is actually the heat capacity at constant volume. So in the end I have that my variance of energy is actually equal to the product of Cv times kb t squared. That's the end. So if you know, for example, if you know heat capacity at constant volume, then you can easily calculate the fluctuations of energy. What's good about this, that you actually don't need to know the partition function, you just need to know this single variable. So what is good about this equation is that you can calculate fluctuations from thermodynamic variables. So in thermodynamics, you can determine the heat capacity using some experiment, while there is no experiment which allows you to determine fluctuations. Well, of course, you can do some measurements, but in the case of energy, it's quite difficult to measure what energy is, the exact energy in the system is, and that by measuring the heat capacity, you are able to determine the fluctuations of your internal energy. Not only you are able to determine your internal energy, but also its fluctuations. Okay, now let's go to the fifth story. The fifth story would be about the fluctuations of volume. And to calculate fluctuations of volume, I'm going to use some sort of a tentative approach. It's not a rigorous one, but it gives correct results, and which exactly coincide with the calculations using the rigorous approach. So what I'm going to do now, I'm going to assume that I have a certain portion of gas which is inside a very large vessel, and there is a small portion of this gas which is separated from the leftover portion of gas by a piston. And there is some equilibrium position for the piston, and this equilibrium is determined by the equivalence of pressures from both sides of the piston. And for example, if we assume that the temperature of the gas is kept constant, then according to the Boyle-Marriott law, if I change the position of this piston, for example, if I move this piston to this side, then my pressure would decrease, and due to the imbalance between the pressures from the both sides of the piston, there would be a force which would try to reverse the motion of piston. So if I have a displacement to that side, the force would push the piston back to its equilibrium position. So now I'm going to calculate that force. So let's say, for example, well, I can write that pressure. Okay, let's think that we deal not only with the ideal gas, but it can be just about any system, because there is some relationship between the pressure and the volume in the system. And if your system, it can be, for example, a droplet which is placed on top of some surface, and of course for the droplet there is also some fluctuations of its shape and its volume. So we need to be able to calculate everything. So that's why I'm not going to keep my discussion limited only to the ideal gas, but I'm going to assume that I have a system which has arbitrary properties. So in here, what I know is that pressure is equal to the pressure, the outside pressure, or the equilibrium pressure. And now I'm going to do the Taylor expansion of that pressure as a function of volume. So what I'm going to write, that this is actually the partial derivative of pressure with respect to volume at the constant temperature, because I keep the temperature of my system constant throughout all of these fluctuations. And then as I do so, then I need to multiply it by the change of the volume. And in the case that I have, in this imaginary situation in which I have a piston, that volume change can be presented as sum, that's a product of the cross-sectional area of the piston A multiplied by the displacement of the piston delta x. Okay. And usually this derivative is negative, so that's why if my displacement is positive, then actually the pressure becomes negative. And if I calculate the total counteracting force, which aims to return my piston back to the equilibrium position, then it would be equal to the A multiplied by the pressure difference, which is P0 minus P, and which is equal to dP over dV at the constant temperature multiplied by A squared times delta x. So as you see, the whole system behaves as if the piston is a part of is the weight which is attached to a spring with some spring constant K, which is determined as F over delta x, and is equal to A squared times dP over dV at the constant temperature. And now I'm going to apply the Equipartition Theorem to the system. This Equipartition Theorem states that if I have some term in the energy of the system, a square term in the energy, then the amount of energy related to that degree of freedom should be equal to kBT over 2. In our case, since I have my piston attached to an imaginary spring, then of course there should be the energy associated with this motion, and that energy is K delta x squared over 2. And the Equipartition Theorem states that if I want to calculate mean value of this energy, then it should be equal to kBT over 2, which allows me to determine delta x squared. That gives me kBT over spring constant K. And now I can calculate the fluctuations of volume, because the fluctuations of volume should be equal to the piston area multiplied by the fluctuations of x, and the fluctuations of x are square root of the mean value of delta x squared. So that is equal to A times kBT over K, and that gives me A over A is eliminated from here, so that gives me kBT multiplied by the dV over dP at the constant temperature, and all of that to the 1 over 2, to the power of 1 over 2. So I can write that actually sigma V squared is equal to kBT times dV over dP at the constant temperature. Okay, so those are the fluctuations of volume of the ideal gas. And of course, this was only a tentative model, but if we consider, for example, any kind of a system, if I don't have, for example, a rigid piston, then I can assume that I have lots of small pistons everywhere, which separate my gas volume or my droplet from the environment, and each of them moves slightly independently, and then I can accumulate all of this into a single term here. Okay, so that's going to work. Now let's try to apply this equation to the ideal gas. In the case of ideal gas, I can write that, for example, PV equals to nu, okay, RT, or I can write that this is equal to N kBT. So that means that volume as a function of pressure is determined by this equation, N kBT over pressure, and the derivative here is equal to, okay, I should also have minus here, because indeed I should have minus, because it's negative quantity. So everywhere here I should have minus. So that gives me, for the ideal gas, I can write that ideal gas sigma V squared is equal to minus kBT times N kBT over minus pressure squared. Okay, so, well, I can use this once again, and I can say that this is actually equal to kBT times volume over the pressure. So that's the fluctuations of volume. And, well, I can do that once again, that pressure over kBT gives me, actually pressure over kBT gives me N over volume. So this gives me volume squared over N. So for the ideal gas, the fluctuations of volume are equal to the volume over square root of N, where N is the number of particles in that volume. And once again, as we see, we can actually apply the same, that the relative fluctuations of volume of the ideal gas are equal to 1 over square root of N. Well, the bad message is that it's applicable only to the ideal gas. You cannot calculate the relative fluctuations of the droplet volume by this, because as you understand, for the droplet, dV over dP is usually very, very small quantity. So the fluctuations for the volume of droplet are much less than the fluctuations of volume of the gas, which consists of the same number of particles. Okay, now we can also extend this calculation to the now we can also extend this fluctuation to fluctuations of volume at the constant entropy. So in the adiabatic environment, so previously we have considered isothermic environment. Now we can also do the same for the adiabatic environment, and the derivation is pretty much the same. So if I calculate the fluctuations of volume for the adiabatic environment, that would be the story number 6, or actually I can say that this is the story number 5 star. Fluctuations of volume at constant entropy. So if I don't allow any heat to be transferred to the gas, so I assume that all of these fluctuations happen at this like without any heat exchange, not the temperature is kept constant. Well, in this way, actually, I need just to make a small change in my spring constant K. So instead of the derivative at the constant temperature, I can replace everything by the derivative at the constant entropy. So that would give me exactly the same equation. So repeating all of the same stuff which I have done for the fluctuations of volume, I can get that the fluctuations of volume would be actually equal to kBt multiplied by the derivative of V over P at the constant entropy. And please keep in mind that while I have not given some attention to this, but during the derivation there, I have used the fact that 1 over the derivative of partial derivative dP over dV at the constant, well, temperature is equal to dV over dP at the constant temperature. And I assume that this is something obvious for you. And here I have used it too. Well, that ends my story number 5 star, and that brings me to the 6th story, where I give you a hint on the general theory for thermodynamic fluctuations. In other previous stories, I have used the fact that actually that all of my systems obey Gibbs distribution. So if you look at this, in all of these stories, in a certain way, in one way or another, I have assumed that the probability of a microscopic state is proportional to the exponent of minus the energy of that microscopic state divided by kBt. And as I have shown you during the derivation of the Gibbs distribution, this distribution is actually the distribution which maximizes the entropy. So this maximizes entropy. But the entropy by definition is equal to kb times natural log of capital G, where capital G is the so-called statistical weight. So the statistical weight or number of possible microscopic states. And I assume that in my studies, I assume that all of the microscopic states are have in here, well, almost equal probability. So that means that if I calculate the probability for the system to be in a certain microscopic state, and what I actually need to do is I need to write that the probability is proportional to the exponent of S over kb. So now that gives us a general tool, a powerful tool, which allows you to calculate fluctuations for any thermodynamic variable. So instead of using Gibbs distribution, which maximizes the entropy, I'm going to use this notation use the concept of statistical weight. So the probability of a certain state of the system should be determined like this. So and of course, if I have a certain thermodynamic variable x, I can express the entropy as a function of the thermodynamic variable x, and that should be something like the maximum value of that at a certain x0. And if I use Taylor expansion, then what I need to write next? That I need to write the derivative of s over x multiplied by x minus x0. But since I have the maximum, then that should be equal to 0. So there is no linear term. And since I have maximum, that means that I should also write here the second derivative of the entropy over x and multiplied by x minus x0 squared over 2. And of course, the second derivative should be negative, but what's important here is that the probability can be written as exponent of s of x0 over kb plus second derivative of entropy with respect to that macroscopic quantity x multiplied by x minus x0 squared over 2. And this is a perfectly for the negative second derivative. This is actually the perfectly relevant to the normal distribution. So if this is some constant, so it should be taken out of the exponent. So this is some constant multiplied by this. Okay. So that's the general rule for calculation of probability, but please keep in mind that in the case when your system is not adiabatically insulated, then this entropy should apply to the some adiabatically insulated system. So for example, if you consider the fluctuations of volume of a certain system, which is in contact with some environment here, which has some pressure and temperature, then of course that entropy S should be actually the total entropy of your subsystem and your environment surroundings. So sometimes this calculation can be pretty complicated. But well, let's say let's try to rederive that equation for the fluctuations of volume at constant entropy, because that is actually related to the in here I have a adiabatically insulated system which perfectly matches this condition. So I can just calculate the entropy of the subsystem. So let's try to repeat the story 5-star using this more general approach. So let's write the entropy for the system. So according to the definition, I can write that TdS equals to CV dt well, once my entropy is constant in this system, then how can I calculate so then how can I calculate the fluctuations of volume since it's constant? So I cannot do this kind of the decomposition. So it's not going to work in that case, actually. Well, that's pretty bad. Okay, let's try to apply it to some another example. Let's try to use that to calculate, for example, the fluctuations of the particle number, the story number 2. The fluctuations of the particle number in the selected volume of the ideal gas. So in here, I'm going to divide that volume into two different systems, volume V0 and volume V minus V0. And I'm going to describe the microscopic state by the number of particles N0 inside my selected volume and the number of particles N minus N0 outside the selected volume. So what I need to use is I need to use the equation for the entropy for the ideal gas, but I need to use the slightly modified expression. As you know, I have previously derived that entropy of the ideal gas is sum S0 plus nu R logarithm T plus plus CV nu CV logarithm T plus nu R logarithm V. Okay, there is some issue with this definition of entropy. If I want to calculate, so this definition is valid if I keep the number of particles constant. But if I allow for the number of particles to change, then I need to somewhat modify this expression. So what I need to do, I'm going to use the following. So let's, for example, use the following procedure. We know that the entropy is an additive quantity. So if I, for example, separate my gas into two different volumes, then the entropy of these two volumes would be S1 plus S2. So that's the additive quantity. So in here, actually, in order to do this, so I can represent it like follows. And if I continue to divide that quantity further and further and further, I can eventually reach up the case in which I have the number of volumes which exactly coincides with the number of particles in my gas. So I can calculate the entropy as N, which is the number of particles of the gas, multiplied by the function of entropy, which is calculated for one particle, which is located in the volume of V over N. Since my entropy is an additive quantity. So I have just used this property. So in this way, I determine the entropy of the ideal gas in which the number of particles can vary as follows. Now this should be N times some S0, the entropy, the constant entropy per single molecule, plus, okay, in here I have nu CV, so that would give me, so if I substitute that number of particles here is equal to 1, that would give me CV over the Avogadro number. Actually, that smaller heat capacity at constant volume divided by Avogadro number. So this is heat capacity at constant volume per single particle of gas multiplied by logarithm T plus, in here I have just Kb multiplied by logarithm of V over N. Okay, so that's the definition for the entropy in which I can also change the number of molecules. So this one is preferable when the number of molecules in your system changes. Now this one applies only to the ideal gas in which the amount of gas doesn't change. So now I'm going to calculate the total entropy of the ideal gas using this equation. I'm going to go here. So I'm going to get here. So the total entropy consists of the entropy of the gas inside the volume V0 and outside of it. So that gives me N0 times S0 plus CV over N0 times a logarithm T plus Kb, okay, this is T0, plus Kb, a logarithm of V0 over N0 plus the same expression for outside of that selected volume. Plus kb times v minus v0 over n minus n0. Okay, actually in here, over n Avogadro. Here I have over n Avogadro, so I have done a small mistake here. Over n Avogadro. So now if I open all of these brackets and collect all the terms together, that would give me something like follows. That is, okay, that would be n times S0 plus n times Tv over n Avogadro logarithm T0, which is again a constant which can be discarded. It doesn't influence my total value, plus n0 times kb natural log of v0 over n0 plus kb times n minus n0 times natural log of v minus v0 over n minus n0. So first two terms can be discarded since they are constant, but the third and the fourth term actually depends somehow on the quantity n0. So we can actually perform a tailored decomposition. So first of all, we need to calculate where the entropy is maximized. In order to calculate where the entropy is maximized, I need to calculate the derivative of ds over dn0, and that gives me kb times logarithm of v0 over n0 plus kb times n0 multiplied by 1 over n0. So this is actually eliminated, plus the same procedure for the second term. I apply the multiplication rule and get kb times, okay, here goes minus kb natural log of v minus v0 over n minus n0. Finally, okay, and again also I need to subtract kb, which comes from the derivative if I leave this and calculate the derivative of that logarithm, and that would give me 1 over n minus n0, now with the negative sign, and twice. Okay, so here actually I have the minus, and here I have plus kb, but this plus kb and minus kb are mutually eliminated. So altogether, if I calculate the derivative, that gives me kb times logarithm v0 over n0 minus a logarithm of v minus v0 over n minus n0. So if I demand that this derivative equals to 0, that means that these two logarithms should be equal to 0. So that leads to v0 over n0 equal to v minus v0 over n minus n0. And from which I can determine that n0 over v0 equals to n over v. So that means that in order to maximize the entropy, the number density of molecules inside my selected volume should be equal to the number density of molecules in the whole large vessel. So again, this coincides with our previous result during this section 2, which was determined statistically, but now I have done the same stuff, but purely thermodynamically, without any reference to the statistics. Now, in order to calculate the fluctuation of the number of molecules, I need to calculate the second derivative of the entropy. So I need to calculate the derivative of this expression once again, and that gives me the following. So that is the Kb. So I calculate derivative. So this logarithm, okay, this is logarithm v0 minus logarithm n0. The logarithm in n0 derivative is gives me minus 1 over n0. Okay, and here is plus 1 over n minus n0. But actually not plus, but because when we apply the chains rule, here minus logarithm gives me plus logarithm, but I need also to multiply by minus 1, which is the derivative of n minus n0 over n0. So as we have expected here in our previous discussion, as we have expected, the second derivative of the entropy is negative. So in here I write that this is okay. I can actually neglect the second term here. The reason is that if I have a very large volume surrounding me, then that means that the number of particles, the total number of particles in that volume is much larger than 0, and that means that the denominator of the second term is much larger than the denominator of the first term. So out of these two different terms, the value of the second derivative of entropy is determined only by the first term, because the second term is very small compared to the first one. So I can write that this is equal to minus Kb over n0. And now I can write the probability distribution for the number of particles in that volume. Probability is proportional to the exponent of minus Kb. Oops, there is no Kb here because I need to divide this by Kb. In my this expression, I have S over x0 over Kb. So so there is no Kb. So what's left is just n0 minus average n0 squared divided by 2n0. If you look at the equation for the normal distribution, then actually this stuff in the denominator is actually squared standard deviation. So once again, we were able to determine to calculate the fluctuations of the quantity, but now not using the statistical but thermodynamic approach. And that shows that thermodynamics and statistics are very intimately related to each other, because, for example, that expression for the entropy could be derived from the statistical viewpoint. But all of that agrees. So the statistical physics puts the groundwork for, or actually it explains why thermodynamics actually works. Okay, with this I would like to end my lecture and have a very large break of about probably 15 minutes. Thank you for your attention. Okay, hello. As I see there are some people here, it seems like there was some kind of a misunderstanding in terms of announcements for the lecture, because the international department has arranged the video recording for me, but it wasn't an unusual time. It started at 2 p.m., not at 15:30 as we usually do, but at 2 p.m. In my today's lecture, I actually kind of try to get the best of two worlds. I have got the feedback from you about what kind of lecture do you prefer more. The lectures with my live videos or the lectures with the presentation. So for today's lecture, I have decided to do the both. So I'm just trying to make the double voice. So there. Можно на секундочку? Там, кажется, какие-то технические проблемы. Почему-то, наверное, эхо слышится. Эхо пишет. Эхо, да. А у вас не слышно эхо? Вы сейчас есть трансляция? Давай сейчас попробуем. 1, 2, 3, 4, 5. Есть эхо или нет? Интересно. Is there any echo now? In your case? Because I see the complaints about echoes. No echo now. Okay, probably there was, it's okay. Okay, so we can continue. So about the stuff, so I try to make the live recording, and also I would send by the end of this lecture, I would send you the presentation which briefly summarizes most important moments of the presentation, so that you would be able to, for example, resolve the issues if something was written unrecognizably on the blackboard, and you would be able to see it clearly in the lecture presentation. Also, there was a question about the written exam. I have not yet the date for the written exam. As much as I understand, the classes are being recorded. Yeah, it's being recorded. That would be a YouTube live video uploaded to YouTube after this lecture ends. And there is also a live video now streaming on the YouTube too, in addition to this Zoom meeting. So there you would be able to see my explanations and all the details of these derivations. Also, there was a question about the written exam. The written exam would be after we have finished all of the lectures. According to the schedule, we have this lecture, and the next lecture is supposed to be the last one, but we had one probably lecture missing due to the state holiday at 4th of November, as much as I remember. And for this reason, we were not able to do the whole program in all of these lectures. So we need also to have one additional lecture a week. Okay, there would be a lecture this week, next week, and the week after that would be an additional lecture, which I'm going to hold well, remotely. So there would not be a live recording for that lecture. And probably the written examination would be somewhere in January. So you have already the dates for the oral examination, and probably there would be written examination a few days prior to the oral examination. I'm going to discuss that with the international department and arrange the the date of the oral or the date of the written and oral examinations. Okay, so you would have some time to prepare for written exam and the oral exam, and to choose the question of your choice. Okay, so we have already done with the lecture today. That was about the fluctuations, and now we are going to do the seminar. I once again express my excuse for the things which have happened. Probably I should have done the additional announcement from my side, because I was expecting that to be done by the institution. Could you explain about the question of choice? Okay, this is the usual practice. We probably had this in the previous semester. You choose some interesting question like related to thermodynamics, which goes which touches some questions of the program and goes slightly beyond that question, and then prepare the presentation and the talk about that topic. So the aim of the question of your choice is that to encourage you to study somewhat beyond the program. So, and to try to deepen your understanding of the thermodynamics course by studying some interesting aspect of the science, some interesting aspect which you can find, and then it should be one more written exam and oral. You would have two examinations. There would be a written examination in which you dedicate your time solely to solution of the problems in the written form and submit your solutions to me in the written form. And there would be another day. It doesn't necessarily be something numerical. Well, necessarily the problems would be related to the analytical derivations of some closed form expressions for the result, and in some cases you would be required to calculate the numerical answer using your calculators. So the written examination would be pretty much the same as the midterm test. It just would expand the scope of the program which is involved in the problems. Also, in regard to the question of your choice, you prepare, the question, well, the question of choice doesn't necessarily need to be something numerical. So it should be some curious phenomenon. It can be some curious phenomenon, but it should involve some explanation. So if it's just something, look and see, I see there is something strange happening there, it's probably not going to work. There should be some underlying model to that phenomenon. So if you have some kind of an effect, you should also try. We need to send a report before the deadline when. Well, you just need to send me the topic of your question of your choice. You don't need to submit the whole presentation to me. I want it to be a kind of a surprise to me. You just need to submit the topic. You don't need to submit the whole report before. You need to submit topic, and you need to decide on the topic before the oral exam, just not to the deadline is when. And the reason why I require you to send me the topics of the question of the choice, I need to make sure that you don't have overlapping questions. So every one of you should choose somewhat different questions for your question of your choice. In the case when you have really trouble, if you have the trouble of choosing the question of choice, then I think, well, it can be the worst possible idea, but it is also somewhat acceptable. You can choose one question from the program, and you can study that question extensively, and well, that pretty much would determine your mark for the oral exam. Okay, that's about the question of the choice. Well, have I answered all the questions you had to me? About the exam. The date would be chosen further, because as of now I see there is only one date for the examination in thermodynamics. I need to apply for 2 days for the examination of thermodynamics. So I would, after I get some feedback from 2 exams, the written test and oral exam. So it's done in 2 parts. So the whole examination is done in 2 parts. It has a written part and oral part. So, well, the written part is somewhat similar to the midterm test you had. Okay, so that's why I need to assign 2 different dates for these examinations, because one day you need to prepare for problem solving, while the other day you need to prepare for talking with me and prepare your question of your choice, the presentation, and that requires in the oral amount. We also have to solve some equations. Yes, it might be so that I might ask you to some kind of a simple theoretical question. It can be asked while you are delivering me a talk about the question of your choice. So mostly I prefer to ask you some questions related to your reports exactly. So the questions, some basic questions from the syllabus of thermodynamics related to your reports. Also, I have sent you. Oops, there is something happening there. It's 27 seconds before turn off. Okay, so I have sent you a list of the questions, of the simple problems which are mandatory for you to obtain a positive mark on your exam. So you should be able to solve how they calculated. I'm talking about the percentages. So altogether, I'm going to take into account your results of the midterm test, your homework. That means that if you don't have a homework, then your midterm or your mark would be subtracted due to the absence of the homework. And also the results of the written test would give altogether, they would give you the maximum possible mark for the oral test, for the oral exam. And well, if you, for example, fail on your oral exam, then of course I can give you the mark which is lower than the mark calculated from the from your midterm and the final written test. Well, but nonetheless, even if you fail during your oral exam, I would like to give you like some kind of an average in between the your assessment for the answer for the oral examination and the assessment of your work during the whole semester. So I'm going to take into account like how you have done your homework, well, whether you have submitted your homework in time, and also your results on the midterm test. So at the same time, that maximum the maximum mark for the oral test doesn't actually mean that I cannot give you a mark which exceeds that one. If you, for example, give a very astonishing presentation and you are able to answer all of my questions related to your report on the question of your choice, then I might be able to use my positive impression of your answer to increase your mark. So that's why all of the parts of our studies are important. So the important stuff is submitting your homework in time. It is important to have your midterm test and written tests written accordingly. And probably I'm going to give somewhat larger weight to the final written test than to the midterm test. Well, probably that would be like about 1.5 times greater weight than the midterm test, because the final written test is, you can say that it corresponds to your level of knowledge by the end of the semester. So even if I can't, like, for example, name exactly the percentages to you, well, but if you are doing well on all of these sides, then of course the final mark would be great. Even if you, like, for example, have some difficulties during the oral examination. Okay, I think that probably answers all of your questions regarding examination. Of course, I'm going to make the detailed explanation before the examination with the announcements of the examination. Also, I would send you the usual rules. Oh, okay, there is another question there. I don't even see the whole one. Can you just show me that message in chat, because I don't see all of that message. Like last semester, we had 5 points, each from 2 written exams, and 2 points each from 2 homeworks. Well, it can be done in this manner. I can actually, like, for example, assign to your to your midterm test, like for example 6 points to include your homework in your written test, and then and also to do the same with your final written test. So we can do actually. So if you agree with this procedure, then we can do the same stuff during this semester. I don't see any objections here. So you have two homeworks. You add some points from your homeworks. You also have some your performance during the written tests, so that would be also accounted into the final mark. And also, okay, the final mark would be presented during your oral exam. So it would be an aggregate. So we had like 14 points. 14 points by the end of the semester before oral exam. Something like that. Probably I will limit that to 12 points, not to 14 points. At the same time, as I have said, I would slightly adjust your mark levels in accordance to your performance during the midterm test. As I see from your midterm test, there are some common mistakes which are being made, and well, probably I'm going to close my eyes on some of them. Okay, so that's what's going to happen. So I just want to say that if you like prepare well, then I think there would be no trouble in getting a positive mark for the thermodynamics course. Okay, so if you have no more questions about the examination, and also, as much as I understand, I also have a depth of sending your midterm test results. I will try to do this as soon as possible. I had this rush at the end of this year, and well, I think I expect that during this weekend I'm going to submit the paper which I was working on, and then I would just be able to spend my time checking your midterm tests. That would actually pretty much determine the procedure for the final written test and the oral examination. Okay, so now we go to the seminar related to fluctuations. Today we are going to solve problems from seminar number 12, Statistical Meaning of Entropy and Fluctuations. I'm going to start with zero-level problems. The first one would be problem number 26. Two solids with temperatures T1 of 299 kelvins and 300 kelvins. Now are brought into contact. Estimate how many times it is more likely that a portion of energy of 10 to the minus 11 ergs that portion is transferred from the hotter solid to the cooler solid than in the opposite direction. Heat capacities of the bodies are large enough so that the change in the temperature can be neglected. So this problem exactly uses the entropy-driven calculation of fluctuations. So what I'm talking about is that the probability of some process should be proportional to the statistical weight of the final state. So we just need to calculate statistical weight of the final states, of two final states when these amounts of energy are being transferred between these solids. But the statistical weight itself can be calculated as the exponent of entropy over Kb. Okay, this equation should not be a surprise to you, because I have initially determined the entropy as Kb, a logarithm of the statistical weight. So that's why if I want to calculate statistical weight from here, I first of all express the logarithm of g as s over Kb, and then calculate the exponent of both sides of this equation. So I get G equals to S over KB. So now what we need to do is to calculate the entropy in both cases. So let's assume that in the initial conditions, before any transfer of heat has occurred, the entropy of this whole system equals to S0. And as we know, actually the entropy is equal to S1 plus S2. So I can present it as S0 plus delta S1 plus delta S2, where delta S1 and delta S2 respectively are the changes of the entropy of each of the solids. And the increment of entropy of each of the solids can be calculated quite easily, actually. So in here, if I consider first the process in which the heat is being transferred from hot body to cold body, then hot to cold, then the increment in entropy of the cold body would be epsilon over T1, while the entropy of the hot body would decrease by epsilon over T2. But since T2 is larger than T1, the whole change of entropy would be positive. So I can write it as 0 plus epsilon times T2 minus T1 over T1 T2. So altogether that gives me approximately S0 plus epsilon times delta T, which is 1 Kelvin, the temperature difference between hot and cold body, over T squared. T squared, where I can take T equal to 300 kelvins, since there is not much difference between T1 and T2, so the denominator is approximately equal to 300 Kelvin squared. In the case when the heat is being transferred in the opposite direction, then I can write that actually the entropy of hot body increases while the temperature of cold body decreases. So that gives me S0 minus, so the entropy actually decreased in this process, S0 minus delta T over T squared. Okay, so now we are going to calculate the ratio of the statistical weights. So the probability of one process over the probability of the second process should be equal to the ratio of statistical weights. And the way I need to calculate the ratio in which first from hot body the heat has been transferred to the cold body, and divided by the statistical weight in the second case. So that gives me exponent of here goes epsilon over KB times T squared times delta T. And in the denominator I can write it the same exponent but just with the minus sign. Okay, now I can collect all of these exponents into a single expression, and that would give me exponent of 2 epsilon over KB T times delta T over T. So what actually matters in this problem is the relationship between the amount of transferred energy and KBT. So what this expression says, that actually if you consider the heat transfer process, as far as it concerns the amounts of energy which are a very small fraction or just equal to this KBT, then heat can be transferred in both directions with some non-negligible probability. So this is how fluctuations work. You can change the energy of the system is changing by amounts of KBT, so these changes are not producing any violation of the second law of thermodynamics. So in here, well, let's try to calculate this the ratio epsilon over kBt. So epsilon is 10 to the minus 11 erg, and this is 10 to the minus 18 joule, while kBt equals to 1.38 times 10 to the minus 23rd multiplied by 300. Well, so that's actually 1.38 times 3. That's approximately 4. Well, if it's more correct, that would be 4.14 times 10 to the minus 12. Well, not 12, but 21. Okay, now again in joules. Once again, we can see. So we can see now that actually epsilon is quite larger than kBt, but we also have this fraction of delta t over t, which gives you 1 over 300. So altogether, this should be exponent of, here goes 2 times 10 to the minus 18 times 1 over 4.14 times 10 to the minus 21st times 300. Okay, so after I continue my calculations, that would give me 10 to the minus 19. So that would give me 20 exponent of 20 over 4.14 times 3. So that would be exponent of 20 over 12.42. I guess it's something like this. Well, if you calculate this, that would be approximately 5, as much as I remember. That would be approximately 5, and that's the answer to this question. So the probability of the natural process of the heat transfer from the hot body to the cold body is 5 times larger than the probability of the unnatural process of heat transfer from the cold body to a hot body. Okay, now the problem number 27. The problem number 27. A small weight of 10 grams is suspended on a light 1 meter long thread. Estimate the standard deviation of the weight from its equilibrium position due to the thermal fluctuations at room temperature. So we have a so-called mathematical pendulum in which mass is 10 grams. The length of the thread is 1 meter. Thermal fluctuations at room temperature are being considered. Well, and here we have a mechanical system. If we consider the motion of this system as a whole, then the energy of this motion would be equal to, okay, mv squared over 2 plus mgh, where h is the elevation of the pendulum. So as it goes to the side, as it deviates, as its position deviates to the side from the equilibrium position, then there would be some height accumulated in this process, and we can calculate this h. assuming that this angle alpha is very small, then we can write that h equals to L minus L cosine alpha. And then we use the famous expression for the cosine alpha, which stems from its Taylor series, that cosine alpha for small angles alpha is approximately 1 minus alpha squared over 2, which allows us to get that this is L times alpha squared over 2. Or actually I can write it as, so what I need actually to find the deviation. So the deviation. So I need to calculate this horizontal deviation. At the same time, for the horizontal deviation, I can write that this is approximately equal to L sine alpha. So this is approximately alpha L. And from these two equations, I can express h as a function of x. That gives me h equals to x squared over 2L. So as I substituted here, that would give me mv squared over 2 plus mg over 2L times x squared. As you see, this particular degree of freedom introduces two square terms into the energy of the system. So if I apply the Equipartition Theorem, that would mean that actually I can write that for these terms, mv squared over 2 average equals to kBt over 2. And for the second term, mgx squared over 2L should also be equal to kBt over 2. Well, of course, the first one is not relevant for our calculations, but our final result should be obtained from the second equation. And that gives us that average of the deviation from the equilibrium position squared is equal to kBt times L over mg. kBt L over mg. So the root mean square deviation from the equilibrium position would be the square root of this. So that would be square root of kBt L over mg. I think the main purpose of this problem is to demonstrate you that actually Equipartition Theorem for some reason can be applied to macroscopic objects too, since indeed if I consider the macroscopic motion, that also introduces degree of freedom, and we have these square terms in the energy. So Equipartition Theorem can be applied to this. So in terms in regard to the statistics and thermodynamics, it actually doesn't matter much whether you have the microscopic motion or macroscopic motion. So you can actually apply this Equipartition theorem to any system. And probably the second purpose is to give you an estimate of how large these fluctuations are actually are. So for the second purpose, we need to calculate the root mean square deviation. Okay, so now for this calculation, I need to substitute all of the numbers here. So it has 1.38 to the 10 to the minus 23rd times t, which is 300, times L, which is luckily just 1, divided by the mass, which is 10 grams, and that is 10 times 10 to the minus 3rd. So I expect this to be quite a small number, because as you see, if I just look on these tens, then it appears to be quite a small number. So actually the product of 1.38 times 3 is approximately equal, well, we have calculated this previously, That would be just 4.14. This 10 to the minus 23 multiplied by 100 gives me 10 to the minus 21st, but we also have 10 to the minus 2 in the denominator, so that would be times 10 to the minus 19 altogether. So if I calculate the square root, I first need to change the position of my floating point, so it would be square root of 41.4 multiplied by the square root of 10 to the minus 20. 10 to the minus 20. Oh yeah, I have forgotten g, and g would be in this denominator, g would be 9.8, well, which is approximately 10 meters per second squared. So this is actually 10 to the minus 20 here. So 4.14, a square root of 4.14 times this. Well, this is approximately equal to 2 times 10 to the minus 10 meters. So it's actually an awfully small number of 0.2 nanometers. So these fluctuations appear to be really small. Let me see if I have not done any mistake in my calculations. 0.2 nanometers. Yeah, that's exactly. So as you see, if you consider the fluctuations applied to large macroscopic objects, actually this mathematical pendulum consists 10 grams of material. They consist of so large number of atoms that actually the fact that your fluctuation or your deviation from your equilibrium position would be very small can be predicted using just using the square root of n rule. So in here, as you see, the fluctuations, well, the relative fluctuations, they decrease as you increase the number of particles involved. So that means that at the end we have just 0.2 nanometers. Okay, so these are very simple zero-level problems. So now we are going to continue with the more complicated examples from the Irodov book. Probably not so complicated. So let's see. Let's start with the problem T6. So it's not from Irodov book, it's from the syllabus. Okay, that's actually kind of an interesting problem, which is related to the quantum mechanics. The problem T6. A system consists of n non-interacting particles of spin 1 with possible quantum states denoted as m equal to 0 and n equal to plus minus 1. The energy of particles in states m equals to plus minus 1 is equal to epsilon, while the energy of the state where m equals to 0 is equal to 0. Calculate the entropy of the system when 0 is less than epsilon, which is quite obvious, which is much less than kBT. Okay, so now we are going to do this calculation. Now we have a sort of a two-level system, which is actually a three-level system, but it can be considered a two-level system. And now we are going to do this calculation. First of all, well, we see there is some limitation here. So there are actually two approaches to solving this problem. One of them is just to start off from this limitation, and you see that if you have that, if your kBT is much larger than epsilon, then the occupation probabilities of all of these states are actually equal, because this change in energy or actually the exponential factor exponent of minus epsilon over kBt is approximately equal to 1, which leads to the equal probabilities for occupation of all of your states. P0 equals to 1 over 3, and P plus minus 1 also equals to 1 over 3. That actually allows you to determine the the entropy. So in this regard, we can consider that all of these states have approximately the same energy, since the energy difference is very small in terms of kBt. So that can be considered as a triple degenerate ground state. And in this case, actually, we can write that entropy is equal to Kb times logarithm g. And since we have only 3 microscopic states, that give us Kb times logarithm 3. Well, that's a very tentative solution, and it's not rigorous, and I don't even know whether this solution will be valid if I consider this problem rigorously. To calculate the entropy rigorously, we are going to use the standard procedure from the statistical physics. First of all, we are going to calculate the partition function z. And once again, I'm going to write the definition of the partition function, which is sum of exponents of minus beta times EI for all of the involved energy levels. From my ground energy level, which corresponds to m equal to 0, I have just 1, because the energy of that level is 0, so I have just 1. Then I have 2 energy levels, which have the energy epsilon. So from these 2 energy levels, I have 2 times exponent of minus epsilon over kBt. Okay, so that gives me the partition function. Now I'm going to determine the internal energy of the system. The internal energy should be calculated as 1 over z times the dz over d beta. And that gives me minus, okay, I can just, okay, here, this is kBt. I can write that this is 1 plus exponent, okay, twice the exponent of minus beta epsilon. So if I calculate the derivative of this function, I should have first 2 exponents of minus beta epsilon. And since I calculate the derivative with respect to beta, I should multiply all of this by minus epsilon. And also, I should divide this by z, so I should also put 1 plus 2 exponents of minus beta epsilon in the denominator. So altogether, that gives me the following result. Epsilon times, okay, I can write it as follows. 2 over 2 plus exponent of beta epsilon. Okay, in our case, when kBt is very large, that means that beta is very small and that beta epsilon is much lower than 1. I would just keep in mind that beta epsilon is much less than 1. So it's approximately approaching 0. Okay, so now we calculate the entropy. I think I have shown you in one of my previous lectures, one of the best ways to calculate the entropy is you should first determine the free energy of the system. The free energy is equal to minus kBt logarithm z, or you can write it as minus logarithm z over beta. So I can just write that this is minus logarithm of 1 plus 2 exponent of minus beta epsilon over beta. Well, that's not a very beautiful expression, but it would get even less beautiful if you calculate the entropy. As you know, I'm going to leave this kb logarithm t as a reminder. The stuff which you have calculated from a very, very simple assumptions and probably wrong. We will check it later. So the free energy is this. And as you know, free energy is U minus Ts. So if you know the free energy and you know internal energy, then you can easily determine the entropy. Entropy equals to U minus F over the temperature. So I can just write it like this. U is epsilon times 2 over 2 plus exponent of beta epsilon minus F, which is a kBt, okay, minus, okay, now it goes plus 1 logarithm of 1 plus 2 exponents of minus beta epsilon over beta and divided by temperature. Okay, divided by temperature, this is actually, I can say temperature is 1 over kb beta. If I take beta to be equal to 1 over kBt, then this becomes exactly the temperature. So now I get the final answer for the entropy. That is kb times beta epsilon multiplied by 2 over 2 plus exp beta epsilon plus a logarithm of 1 plus 2 exponents minus beta epsilon. Then brackets closed. Now I'm going to calculate this in the limit of beta epsilon, which is much less than 1. If I take beta epsilon approaching 0, then this exponent would become equal to 1. But this would be equal to 0. This exponent would be equal to 1. So altogether, the first term would disappear, while the second term would be equal to the logarithm of 3, which gives me the final result of kb times logarithm, natural logarithm of 3. Well, it turns out that our previous approach for the calculation of entropy worked well. So because we got the same result, kb times logarithm of 3. So if you have a temperature which is much larger than the energy separation between your energy levels, then from the point of view of this thermal energy, all of these states are kind of degenerate. So you can just assume that all of these states which have the energy separation much lower than kBt can be considered as the states with the same exact amount of energy. So that's the main message of this problem. And since we have done with this one, we can go to the next one. The next one should be somewhat easier. That's from Irodov, 2.154. Okay, the problem 2.154. N atoms of gaseous helium are enclosed in a cubic vessel of volume of 1 centimeter cubed. Find the probability of atoms gathering in 1/2 of the vessel. So let's assume that my vessel is divided into 2 halves by some imaginary plane. And we need to calculate the probability of all the atoms gathering in 1/2 of your vessel. Well, actually, you can imagine a more a more stressful situation. For example, while you are sitting in the room, for some reason, all of the air atoms gather in one half of the room, and this half of the room happens to be not the one in which you are sitting. So in that way, you will be left without air to breathe. So that would be a really stressful situation. We need to calculate the probability of such an unfortunate event. Okay. So we need to remember something from combinatorics when we do this. From the combinatorics, the part which allows you to distribute all of the all of the atoms or the molecules in different boxes. So we have that problem started in the beginning when we have n boxes and we have m balls, and I needed to calculate the number of possible ways to distribute these m balls in n boxes. This is probably somewhat related. So let's try to calculate. So let's assign some numbers to these molecules. Now, molecule number 1, molecule number 2, and molecule number 3, and so on and so forth. So let's now calculate that all of these molecules have gathered in one half. Well, I think we can do this even without this problem. It's just that the probability for the single molecule to be in the chosen half of the vessel is 1/2. But if we calculate the probability of n independent events, that n molecules happen to be in the same half of the vessel, then it should be exactly equal to this small p to the power of n. So that would be 1/2 to the n for all molecules to gather in the same half of the vessel. So if n, okay, we don't know yet n, but we need to calculate the approximate numerical value of n, ensuring the occurrence of this event within the time interval of 10 to the 10 years, which happens to be a lifetime of the universe, the age of the universe. Okay. So as you see that if I just randomly drop molecules into my vessel, then the probability for them to gather in one half is this. What I need to actually calculate is the number of these experiments. So actually, the molecules move by themselves; they change the positions, and it turns what I actually need to determine is the number of, well, coin flips, so to say, occurring at the age of the universe. So I'm going to consider the following. That actually, if I, for example, determine the position of each molecule at a given moment of time, I know where each molecule is located, whether this is located in one half of the vessel or another half of the vessel. If I wait for a very small amount of time, then the molecules would displace only slightly, so that would not allow them to change their positions, to change the half of the vessel in which they are actually residing. So I need to wait quite enough time in order for the molecules to change their positions in the vessel considerably. And the time difference between different coin flips should be approximately equal to the length of the side of this vessel divided by the average speed of the molecule. So if my molecule on average has this speed and my vessel has this side, and if I wait this amount of time, that means then the final position of each molecule would be completely uncorrelated to the position of these molecules at the initial moment of time. So that's what I need to find out. This amount of time happening between two coin flips, so to say, and that is actually equal to 1 centimeter over the thermal velocity, which as we know, is equal to 8 RT over pi mu. Well, I'm not going to go into exact calculations, as much as I remember that the average speed of these molecules is somewhat related to the speed of sound. And of course, this is helium, so the molecules are quite, so the molecular weight is only 4, well, this is about 5 times smaller than the molecular weight of air. So I would say that approximately the value in the denominator would be approximately equal to something like 500 meters per second. Probably there is some mistake in that, but I can say that this is about 500 meters per second. So that gives me the amount of time before the complete randomization of position of molecules of about 10 to the minus 4 over 5. So that would be 2 times 10 to the minus 5, which is 20 microseconds. 20 microseconds. So I would say that redistribution of molecules occurs each 20 microseconds. And I have 10 to the power of 10 years. So that gives me an immense number of molecular position redistributions. Oh, it's almost time to end the lecture. So I'll just calculate the final result. So I need for my 2 to the power of n to be approximately equal to the t over these 20 microseconds. Okay, 10 to the 10 years gives us 365 days times 24 hours in each day, 60 minutes in each hour, and 60 seconds in each minute. And that divided by 20 to the 10 to the minus 6. Well, that's a very large number, probably something like 10 to the, well, that gives me 3. That gives me 180. That gives me 48 times 100. So this is approximately 50, so this is 5,000. 5,000 by 400 approximately, that would give me 200,000. 5,000 by 5,000 by 400. Well, that would give me approximately 2 millions. So I would expect that this is approximately 10 to the 16th power. Yes, and then once again 10 to the power of 6, that will give me 10 to the power of 22 approximately. And this should be approximately equal to 2 to the n. And how do we calculate the n? Is the logarithm base 2 of 10 to the 22. Well, that's approximately 22 times, okay, times 10 and divided by 3. How do I calculate it? I just know that 10 to the power of 3, which is 1,000, it's approximately equal to 1,024, which is 2 to the power of 10. So that means that this is 1,000 to the power of 22 over 3, and each 1,000 gives you 10 to the n. So in the end, that gives you about 60 molecules. It's just, well, it might be, well, not 60, it's 70 molecules. Well, so if you just have 70 molecules, you need to wait for the lifetime universe to let them gather in 1/2 of your 1 cubic centimeter. So that means that the probability of the event that you are left without air in the room is negligible, even if you wait there for the lifetime of the universe. Okay, I think we have 3 minutes for the last one problem. Let's say that would be 2.155. Find the statistical weight of the most probable distribution of 10 identical molecules over 2/2 of the cylinder's volume. Statistical weight of the most probable distribution. Okay, as you might be able to understand now, the most probable distribution of 10 molecules over 2/2 is when we have 5 molecules in 1/2 and 5 molecules in another half. So that is actually the number of microstates corresponding to such a microstate is approximately equal to n factorial over 5 factorial and 5 factorial. So if I name all of the molecules, molecule number 1, number 2, and so on and so forth to 10, then all of the permutations of these 10 molecules can give me each microstate, because if I assume that first 5 molecules are in the first half of the cylinder and the leftover 5 molecules are in the second half of the cylinder, then that's the end. So I get my microstate. And of course, my microstate wouldn't change if I change if I make a permutation of molecules within these 5, here and here. So I need to divide by 5 factorial twice. So that's the statistical weight. Okay, so this is actually 6 times 7 times 8 times 9 times 10 over 2 times 3 times 4 times 5. And this can be actually quite easily calculated, since this is 10 is subtracted here. In here I have 3.4. So let's say 3 and 9 gives me 3. 4 and 8 gives me 2. So 6 by 6 by 7, 36 by 7, approximately 260 something, or probably 70. So that's the statistical weight. Well, of course, this should be calculated rigorously, and the rigorous calculation gives you 252. Okay, so with this, I would like to end my seminar. Thank you for attention, and see you next time. Please watch for the announcements, and probably that would be at the same time, so, and using the same link. So I would be happy to see you again during the next lecture. Thank you.